In this one page of notes, I'll be covering the properties of the equilibrium constant, which really is just different ways to calculate our new K value that I'm going to call K prime, or equilibrium constant called K prime, from the original K or equilibrium constant. There are three ways that we can do this. One is by reversing the equation, two, multiply the coefficients, and three, combine two or more of the reactions, or to be honest with you, you can put all three of these really into one problem. This is part of Unit 7 in AP Chemistry on equilibrium, but it also could apply to your college level course on equilibrium in general chemistry. All right, so let's get started with our reversing the equation example. Off to the side, I have kind of what's going to happen numerically to our new K prime, but I'd like to prove why that occurs. Okay, so first off, let's just take this equation and then reverse it. So 2 ammonia are going to then, moles of ammonia, I should say, are going to then create 1 mole of nitrogen gas. So it's the Haber process sort of in reverse. And then the 3 moles of hydrogen. This would have its own equilibrium constant. We'll call it K prime, an equilibrium expression, where we have the partial pressure of the nitrogen times the partial pressure of the hydrogen, but then cubed, and then the partial pressure of the ammonia, but then that one is squared. All right, so that's the new K prime. And then how would that compare to the equilibrium expression for the original equation? And that one would have your pressure of your ammonia squared, your pressure of your nitrogen, and then partial pressure of the hydrogen. So all these are partial pressures. So you can see that we just have sort of like the reciprocal of it. So if the Kp value is 4.3 to the negative 3, our K prime value, and I'll just do the math kind of over here, you can see that our K prime value is just going to be by taking 1 and then divided by the old Kp, which is 4.3 times 10 to the minus 3. So this is just 1 over the original Kp. And then this gives us the numerical answer of approximately 230 with just 2 sig figs. So it takes a reaction that is, we'll call it reactant favored, and then this one is product favored. And I have that in a separate video before 7.6. All right, so the next one would be, what if we multiplied the coefficient? So I actually did 2 things with this one. I'm going to have us reverse the equation, and we're going to multiply it up, okay? So our new equation that I'm going to have is going to be double the moles and reverse. So I'm going to do both this time. So it'll be 2 methanol as a gas, and then making 2 moles of carbon monoxide as a gas, and then 4 moles of hydrogen. So I'm going to do both with this one just to make this problem a little bit more difficult. So again, how does that give us a new Kp value? And then what is it? So again, I'm just going to write the equilibrium expressions again just to compare. So this is our new Kp equilibrium expression. So we're going to have the partial pressure of CO squared, the partial pressure of hydrogen to the 4th, and then the partial pressure of the methanol, and that one's squared. And then if we compare that to the original Kp above from that equation, this is the equilibrium expression, you'll have the partial pressure of the methanol in the numerator, and then you'll have the partial pressure of the carbon monoxide, and then times the partial pressure of the hydrogen, and then that one would just be squared. So what did we sort of do to this new K value? Well, we have the reciprocal, but also we ended up taking it times 2. So this new K value is going to be kind of 2 changes. Just did this to make the problem harder. So it's going to be 1 over the original value, which was 2.4 times 10 to the 4th. But then we're also going to have to square it. So what happened to this K value, let me see if I can just make this one a little smaller here. There we go. This new one is basically 1 over the original, and then also, but then squared, okay? So not times 2, the coefficients were times 2, but it'll be a squaring effect of the value. And then if you get your calculator, this ends up being 1.9 times 10 to the negative 9th. So again, we've kind of have a very different K value based off the original. In the original, we had it being product favored, and now we have this one being reactant favored. All right, on to the kind of the hardest one. And I did a couple changes again just to make this one a little bit more challenging. When we combine the equations, we actually will multiply the K values for each reaction, but I also wanted us to do a couple changes to each equation just to sort of make this one more difficult. All right, so let's zoom in and take a peek at this last example here. So this is going to be combining two or more of these equilibrium reactions to make an overall. So this is our overall, the one we want, and then our Kp value for that, or K value. I'm just going to call it a K value this time. And then what I'm going to do is just fix the reactions, okay? So the first thing we have to do is take reaction 1. I'm just going to put RxN1 just to make this go a little faster. And for that one, we are going to end up multiplying it by 2. So we're going to have 2NO. I'm just going to also skip states of matter, 1 bromine, and then we're going to have 2 NOBr. Now the reason why I did that is because our final equation, this one right here, okay, that one had double the amount of the NOBr. All right, so then what did I do to kind of have a new K value for this one? It's kind of almost like a new K prime 1. I'm going to take the old K value and then I'm going to square it. Reaction 2, what do we do to that one, or what are we going to need to do to that one? We're going to need to reverse it, and again, I'm going to skip the states of matter. And then we get 2NO. And the reason why I did that, just make this NO a little bit better here. The reason why I did that is because we have to have nitrogen and oxygen as reactants, also bromine. And then we have kind of that intermediate, that's from unit 5. So we have something that's created and then consumed, called an intermediate. If you haven't done unit 5, that's part of that topic in AP chemistry. And then last but not least, we did 1 over the original K. So our new K2 is 1 over the original. So what we're going to do then to find our new overall K is we have to take our K1 and then kind of our K1, what we did to it, and then K2. And what I did to those is I took the 5.3, oops, 5.3, got excited about the decimal place there, I guess. All right, so then that's this one, okay? But then I took that and I squared it because I multiplied the coefficients by 2. And then the other one, I reversed it, so then I'm going to take that and 2.1 times 10 to the 30th. That is a very large K value. In a previous video, I talked about magnitudes of K. And this is one where you could say basically this runs to completion. Most people would probably say it's a one-way arrow versus an equilibrium. But the reverse of it is going to be very low product production, meaning it essentially almost doesn't look like it even happens or occurs. Okay, so then when you multiply these two together, just have to trust my math, that we get the value of 1.3 times 10 to the negative 29th. So overall, our new K value, I'm just going to box that one out since we have a lot of numbers and things floating around here. That new K value is very low. So I would say that this reaction right here is barely occurring. Essentially, it's not occurring much at all. It is making some product, but it's got a very small K value. So I also wanted to cover, since the magnitude of K was the last section, kind of look at the different K values that we have here in this video and compare them to what the 7.5 topic, which was magnitude of K.